Our next speaker is Cheol Hyun Cho from Seoul National University.
Thank you very much for the invitation. Okay, so just stop me anytime if you have any questions. So let me give 3 examples before we discuss something. So this is just to show you that it's not something too complicated. So I'll give you 3 examples of mirror symmetry between between the space and singularity. So this is P2, which has kind of a map to this triangle, and in this case, the mirror is given by this polynomial. And the last example is this pair of pens, and W is XYZ. So this W is regarded as a Coulomb function from C star to C. This is C star squared to C, and this would be from C3 to C. Right? So our first topic is this W as a disk potential function. So schematically, we have Lagrangian submanifold, and we are looking at holomorphic disks. So these are disks on the ambient space, say X, and with boundary on the Lagrangian submanifold, and so we're going to count this kind of thing and to define this W, right? So in the first case, we look at this vibration over interval, and a generic fiber is a circle. Circle is and we're going to count disks with boundary on the circle, and there are obvious ones. There's this red one, and there is a blue one. There are 2 disks, okay? And so W is going to be the sum of all possible classes of disk classes, some count of the disk, and we have some formal parameter, Novikov parameter, which records the area of the disk. So this is the area, and often Lagrangian submanifold is equipped with this is complex line bundle. Unitary or with some connection. Okay.
So, so
yeah.
What do you fix when you say you can define W?
I fixed Lagrangian submanifold. So this W depends on L.
What is the last expression?
That's we have a complex line bundle with a flat connection. So this flat connection. So you can ask, so somebody, on each point you have this complex line bundle. So as you go around, you can ask how the connection moves the line bundle, and that's the holomorph.
So non-zero conversion.
Non-zero conversion, yes. So often you require it to be U1, so that would be U. length 1. All right, so this is the definition. And let's see how it works here. So we have kind of one disks up to automorphism, and so it's one.
The fiber, you fix the fiber. You don't
Yeah, let's fix this fiber at, let's say this is from 0 to 1. Let's say this is U, fiber U. This is fiber S1. Okay, the fiber. I fixed U. Right? And somehow the area of this red one is proportional to U. The area of the blue one is proportional to 1 minus U. So it's T to the U. And 1 T to the 1 minus U. And let's suppose that the holonomy, as we go around this, is holonomy is e to the 2 pi I theta. So here I have e to 2 pi I theta. And then, so because the blue disk is somehow is the opposite one, so you have the opposite orientation. So the holonomy is going to be e to the 2 pi I minus theta. All right. Okay. Let me increase the length of this interval to a factor A. Then, well, if you substitute the first one by z, then this is z plus e to the a divided by z. So this variable z, you think of it as the real part. Somehow this is the real part. Somehow look at the location of your fiber. The imaginary part somehow look at the holonomy around this circle. That's how SYZ works. So you think of this as except the end 2 points. Think of this as a circle vibration, and as you move along the circles, somehow because we have these singular fibers, now you kind of consider this kind of holomorphic disks whose boundary is at the circle. Somehow this red disk is looking at this singular fiber at 0, and this blue circle is looking at the singular fiber at the other end. And they give rise to this potential. Any questions?
Yeah, I have maybe a good question. So this is somehow a counting function, yes?
Yes.
This is a counting. We put a variable, but then this is like a monetary series of counting function. But on the other hand, it's used as a function. That's a plus.
Right. So what is the question is what is the domain, right? So implicitly, well, first I fixed L, but then now I kind of move there. So the space C star. Somehow I kind of make the real part. I think of it as some kind of the base of this SYG vibration, and this circle direction as of this holonomy parameter. That's kind of how usually SYG interprets the mirror space. So SYG claims that mirror is given by dualizing the torus vibration. So the kind of location of our fiber doesn't change, but the dual torus can be interpreted as a holonomy along the torus. So that's the dual torus. Okay. All right. So how about the second P2? It's almost similar. homogeneous coordinate, so let's fix a torus. So let's say the first coordinate has length 1, the second coordinate has length a1, the third coordinate has length a2. Okay, then in this moment map, sure, it corresponds to some point in the interior. So this is a torus fiber. So this is T2. And well, what are the holomorphic disks? Yeah, so this is holomorphic, or usually J holomorphic disks.
So what your map mu is completely doing?
Which one, mu?
Yes.
Mu is just this is called Bowman map, and it's just precisely xz1 squared divided by sum of zi squared. Z2 squared divided by sum of zi squared. And their sum is less than 1. So it's here and it's positive. This image hits here, and there is a circle action. And it's invariant on this torus action, so this is a torus fiber. And the holomorphic disks are like Z, A1, A2, or 1 A1Z, A2, A1, A2 are constants, 1 A1, A2, Z. So Z, you think of it as a variable on the parameterizing the disk, and so these three are the standard disks with whose boundary is here, right? So if it's confusing, just say A1, A2 is 1, so it's Z11, 1Z1, 11Z, right? So there's 3 disks, and so image of 3 disks looks like this. 3 disks like this. All right, and so up to autumnal prism there are these are like there is only one. So W of this torus T2 is 1 times T to the area. The first okay. So this one is easy. So this has area A1. The second one has area A2.
So this means what? So it's complex two-dimension or real?
So this one. This is this. This is what we are counting, and I'm thinking of this. So Z11 as a map from D2 to D2. Holomorph. So this somehow the projection image, the length of the projection image is the proportional to the area, and the third one, and the first one, if you say this has length A, and this is A minus A1 minus A2, and if you decorate with holonomy parameters, E to the I zeta 1, E to the I zeta 2. And the third one, this one, you can also write it as 1 over z, 1 over z. So somehow the holonomy parameter is e to the I zeta minus zeta 1 minus I zeta 2. Again, writing this by z1 and z2, we have z1 plus z2 plus t to the a divided by z1 z2. So if you think of this as a singularity, then this is like a complex parameter. But this, if you think about where this a came from, a came from some size of the symplectic form, we define this moment map. I mean, the size of the P1s, and so this is somehow symplectic data, and in the mirror, it looks like a complex data because this singularity is changing if you change this number. So that's how it's transformed. And the third example, so we are going to wrap around kind of a curve around this pair of pens. So yeah, this, and I'm going to label this angle x, y, z, and the discounting function will count this triangle. So it's W is going to be count of this triangle. This 1 times now.
So Cheol Hyun, what is an analog of mu in the third case?
Analog of mu.
Yes.
There is no mu. Okay, so let me say. So you can think of this as a circle vibration. And in the middle, you have something very singular fiber. Right? So you have 3 very bad drawing. And so I guess we could say that SYG vibration looks like this. So you have circles coming in these 3 directions, and in the middle you have something to singular. So if you kind of shrink this to 2 of these, front and back, that will look like this. But yeah, so the funny thing is that this if you're using SYZ, then you need this whole vibration. But if you're using this immersed Lagrangians, so this L immersed Lagrangian, then this is powerful enough so that it can actually, you don't need these fibers. I mean, it can actually see the whole space. Anyway, so we'll see how it goes. Anyway, so now the counting is, we are not using this formula anymore. Instead, we record like the corners of this. So now we are kind of allowing, in the case we are using immersed Lagrangian, somehow this self-intersection points has these labels x, y, z, and now we are counting these corners, and the labeling of corners is in this case x, y, z. Gives the lambda visible potential. All right, so these are the examples.
That I didn't understand how to generate the function.
Even this one. Yeah. So let me. Yes. So this is just to just keep it in your head. So what is going on? Now we'll start from the more algebraic.
But
or
the
geometry.
You used to generate a function x times y times c.
So this. Okay, so I guess if I write the formula, I would say n beta for all kind of classes beta, and then times like decorations times pt omega. Maybe with holonomy. So I'm just adding this kind of decorations and allowing not only the smooth disks, but allowing some corners. So I just think of this as decorations. X, XYZ decorated disk in the front and on the back. So, okay, so when you have a Lagrangian submanifold, L in our symplectic manifold, so you imagine this either this circle, torus, or this immersed Lagrangian, then we have an infinity algebra. This is a graded vector space with MK, like from k-fold tensor product to V of degree 2 minus k. But in fact, it could have some when it has these contributions, then this guy has a slightly different degree. It's minus mu of beta. This is what's called index, Maslow index, but let me not mention it. Anyway, so there's some infinite algebra. I think it's a kind of generalized version of associative algebra. And okay, so
what is beta?
this beta is the so MK will have this kind of decomposition where beta is a disk class.
Those are the weights.
So this kind of beta is a class in I2 and XL. So it's disk classes. So MK0 is going to be the standard, maybe standard D or boundary in homology or cohomology, and M2 K equal 1. So this will be cup product, K equal 2, and this is the standard cup product. In the other case, 0.
So what is the meaning of the disk here? So what do you mean on the disk now?
What?
What do you mean on the disk now?
Whatever is needed for different engineers. So for smooth algebras, it really means disk, but for immersed Lagrangians, you kind of allow. Well, I mean, in general, in higher category.
No, but it's no longer of real dimension too, right?
Which one?
If you say disk, so your disk. That's my question.
That's no, it's still actually think of it as a map from disk.
Boundary is mapped to boundary.
Boundary is always mapped to Lagrangian, or
So this
either smooth or immersed.
so you puncture at the boundary where the two Lagrangians meet, and now you say that when you have immersed Lagrangian, you put some corners in the boundary.
Right. So
With some.
right. So in general, if you have higher category, then you would have some Lagrangians, and you look at kind of disks with Lagrangian boundary conditions with corners, and then you would interpret this as an operation of alpha 1, alpha 2, let's say alpha k minus 1 to alpha k. So this is the mk minus 1 of alpha 1 to alpha k minus 1. So that's the general category way of defining MK operation. And for most Lagrangians, so this already exists for one Lagrangian. And API identities are nothing but when you have so for any, suppose you have any n elements in the vector space, then for API identity, you take any collection of consecutive k1, and then take the rest of them, k2, with from the output of and also the output of mk1, and then you take the sum of the sign, and this should be 0. So this is the API equation. And this corresponds to, so whenever you have this kind of x1 to xk, whenever you have this mk, this is mk operation, then this degenerates into so this is mk1 and this is mk2.
We have infinity algebra over which field or ring?
Thank you. So we're allowing this formal parameter t, so we have this Novikov ring. But we kind of allow this area to go to infinity, because we could have infinite sums whose area goes to infinity. So, and this is called Novikov ring or Novikov field, and yeah, that's our base. So just you can think of it as polynomial ring, but then a polynomial on T, but then I allow some infinite sums where lambda is equal to infinity.
What is V here?
V is a graded vector space.
Which one?
You mean in the okay. Depends on.
Yeah, but you
So
have
you
symbols
could-
that it belongs to V, so we should know.
So you could say you could start with, in the smooth case, you can define them on the run or some singular chains or Morse. In the immersed case, I will say the Morse version. So L is immersed. Then we is generated by, let's say, Morse complex plus for each immersed generator X. So whenever we have an immersed intersection, if there is X, the complementary angle is called X bar. So we have X and X bar. So we add for each intersection point.
So what does this mean?
What does this mean?
L is immersed, and then you have immersed generators. What does that mean?
So what I mean is, this case, this is just immersed circle. So this is an immersed circle. So what is V? It has 8 generators. First, there is a point class because this is a circle. So circle has a point class and fundamental class. And there are 3 immersed generators X, Y, Z. And so at each intersection, if this is X, the complementary angle is X bar. So you have X bar, Y bar, Z bar. there is the point class and fundamental class and x, y, z, and the complementary angles. This angle, y bar, x bar. Does it make sense? And notice that so why is this is actually very effective, very good Lagrangian, because the vector space is isomorphic to the exterior algebra of on three generators. So this is so these x, y, z are E1, E2, E3, and wedge product of x, y is z bar, wedge product of y, z is x bar, x, z is y bar, and wedge of x, x bar is this is homologically this is one side. Wedge of x, x bar is point, y, y bar is point, z, z bar is point.
So why is y comes the bar? Why is z is x bar? Why how we open?
What is geometry? So okay.
You see that so the product structure.
Right. So let me switch to ordering. X, y, z, x bar, y bar, z bar, and so what I'm saying is I should be more organized. What I'm saying is M2 of x, y is z bar because so there's x, there's y, this is z, and the complementary is z bar, and from this rule here, from this rule, so this triangle defines M2 of x. So product of x, y is z bar, gx is y bar, I see.
So I think I am starting in more basic.
So
Even in the smooth case, so you say that E is, let's say, the Morse complex, a bit finitely generated. So how do you define the iterations? How do you,
okay. So
how do you use the pseudo-holomorphic disk to define the iterations starting from the Morse complex?
So let me first do it for drum, and then for drum, you consider the moduli space of these disks. With mark points Z1, Z2, up to Zk, and Z0, and so these are mapping to X right now. Consider the moduli space, and you do the suitable compactification, and then you look at evaluation map at each mark point. So Z1 lies on the Lagrangian L because this is Lagrangian boundary valued disk. Z2 also lies in the disk, and Zk lies in the disk. And you consider evaluation at 0, that's also on the Lagrangian. And this is whenever you have x1 through xk, kind of living on x1 is a differential form L1, xk is a differential form on Lk. Then pull back, push forward. Using this moduli space. Okay. But geometrically what it means is you think of these as restrictions. You look at disks intersecting the Poincare dual of x1 through xk, and then look at how Z0 moves around. Look at the image of the disk. In the Morse case, you consider some Morse flow intersecting disk, and then all right. But the most difficult part is to make sense of this. Because, details. All right. So, so when we have this infinite algebra, so we say E is a unit if so product it behaves like a unit, but of the sign. And then for all other infinite operations, this is 0. So the intuitive explanation of this is, so this E is like the fundamental class. So this is like redundant condition to intersect. So somehow it doesn't contribute. And so degree 1 element is called Marakatan element. If you have, sometimes you could have M0, so let me just write M0 or M1B. If you're not familiar, you can just ignore M0. Okay, B. And usually in this setting, we want to consider weak Marakatan. That means, so Marakatan is this being 0. Weak Marakatan is this being some multiple of unit. The unit of L. So in this pair of pens case, M3 of so what is going to be D? So this is the degree 0, degree 1, degree 2, degree 3. So, well, this is point, but according to this wedge product, it behaves like this, and so we want, so for Marakatan, we always want degree 1 class. So let's say B is linear combination of X, Y, Z. To consider arbitrary linear combination, I introduce some formal variables, small x, small y, small z. And this small x, y, z has values in lambda. If you have suitable finiteness, then you can have them on as complex numbers. In this case, you can actually say that they are complex numbers. Then this equation boils down to two identities, which is M2 of BB should be 0, and M3 of BBB is XYZ times identity. You can see that, so this is X, Y, Z, then the output is here, and you're really looking at this edge of the triangle. And by permitting all X, Y, Z, you look at all possible edges, and that's somehow how you get a fundamental class. And the decoration, so these numbers come out as a decoration. So these formal variables, I call them decorations. And still, we need this condition. And all the rest are 0. All the rest are 0. In particular, this is non-trivial, but 0, you see that product of xy can become z bar. But product of yx also becomes z bar because there is a triangle on the back side with opposite orientation. So we have x times y is z bar and y times x is z bar. So that's somehow the sign is off. And so for this to work, you actually need to give some non-standard spin structure or maybe non-trivial -1 holonomy. So maybe just say -1 holonomy.
If you have cancellation, one of them should be negative.
Yeah, so there is no cancellation. So in fact, this one does not satisfy, this one does not have a solution. So instead, we need to consider a line bundle version where somehow holonomy, the holonomy is -1, then these two cancel. So, okay, so let's skip this technical difficulty, and we can make this work. So we can make them cancel. And like this. All right, so this is how we define this W. So make an equation. So degree 1 class, look at all possible expressions coming out of this class and write it as.
What is key value stop?
What is
M1 plus M2 plus MK.
Oh, sorry. Keep going.
Keep going.
Sorry. And it could be an EPA sum, but we have not got parameter.
I do not understand the logic here. You're defining WB, or you're saying if you have WB, then you call B an MC element.
So if this expression, this sum is a constant of the unit, then we call it Markov element. And the particular constant is called maybe potential value. But now, because we are doing it for arbitrary coefficients, so you can think of it as a function of x, y, z.
And how do you find? So you have a space of Markov elements.
Yes, the
where
space of
the-
Markov elements are like lambda cubed. Because x, y, z, you can vary x, y, z. So these are all Markov elements. And W is a function defined on Markov.
Here depends on L, and then the W is independent of
W, yes, so, yes. So Markov, if this is a multiple of EL, and this particular multiple is defined as W.
L, it's not unique.
L, we choose this immense Lagrangian. In the case of immense Lagrangian, it's enough to choose one Lagrangian.
So you start with the Lagrangian, then you create the algebra, then you take the Markov element,
Fixed algebra,
and then
everything is out.
Yes. So Lagrangian, infinite algebra, Markov element. So the Markov space is the mirror space, and this number as a function on this Markov space is the potential function. Is it okay? You don't look satisfied. Okay, so now, so this is now we can now easy part from now on. So this works in general. Well, I'm using this example because these torus examples, you need to exponentiate this variable somehow, and so that looks. But so this one is actually easier to understand as you go on. And usually Markov-Tan elements are used. I mean, they arise when you consider deformations, and the deformation, this z, let's say this inverse variable z, we think of it as a parameter kind of looking at this deformation, this surgery, and how much surgery you will do to deform. So you can think of it as deformation parameter. All right. So this is so now we have the singularity. So what are the critical points? So critical points of W corresponds to non-trivial flow cohomology of L in some sense. B deformed. Sorry. So
the deformations of what? Of L?
yeah. So yes, that I didn't explain yet. So informally, I think of it as deforming the actual Lagrangian, but like whenever we have this Markov-Cartan element, you can define a new infinite algebra called MKB, where MKB of x1 through xk is sum of all possible expressions of you insert b and x1 and insert any b, x2, xk, all possible expressions. And this defines a new infinite algebra. If B is Markov-Cartan element.
Weak Markov-Cartan.
Or weak Markov. Yeah, the reason is, I mean, you can imagine that so you're taking two of M operations, and as I said, I mean, the infinite operation was like taking arbitrary two, but this MKB takes particular ones which contains, it has to contain XK. So there are missing ones. The missing ones are the kind of MKs only containing Bs, and this weak Markov-Cartan equation is if you collect all possible Bs arising in this way, that's like a unit, and this whole, when this is a unit, this thing kind of disappears. So that's kind of the reason why it defines the deformation of the infinite algebra. So if you have a Markov-Cartan element, we have an explicit deformation of the infinite algebra, right? And in particular, what is M1B? The new differential is sum of all possible M, B, X, B, B. So if the number of B's, I mean, yeah, it's like K plus 1, number of B is K. So you don't, B may not appear, or just 1B, 2B, and in either side, and so on. So this is M1. So this is actually a simpler calculus, not even a calculus. So suppose you take a derivative of WB. Then this is a derivative of sum of all possible expressions of B's, and taking M operation of that. And this derivative will hit one of the inputs. And when this guy, so this, let's say B is sum of xi, capital Xi, where xi are the basis of the degree 1 generators. Then when we take derivative of 1 over Bi's, you get.
Now when you say degree 1 generators, you are implicitly assuming that all the degree 1 part is more Cartan.
Yes, I'm assuming, yeah, assuming. So let's assume that all these are Markatan, like in our example. Then taking derivative is like the derivative hits one of the b's, and one of the b's become xi, and this is in particular m1. This is m1b of xi. So the critical point means xi cycles. Xi is m1b cycles, and at the end of the day, you can actually prove that with some nice conditions, xi are not boundaries. So flow homology, so M1B homology is not zero. This you need some additional argument. So if it's a critical point, then this has to be zero for all I. That means you have a lot of cycles. And if you use this exterior algebra structure, if you go all the way, you get some point class, and then you can show that the point class cannot vanish. So something like that. Anyway.
But when you say interior cohomology of the Lagrangian, so
yeah, M1B.
In my understanding, to compute Floer cohomology of the Lagrangian, I define the Lagrangian a little bit, so it has finitely many intersections. So
right. So we already have this infinite algebra, so I'm just saying that that's M1B cohomology
of that.
Yeah, M1B cohomology. This B deformed is M1B cohomology. So critical point somehow detects non-trivial flow cohomology. Simple algebra. Once we have this Markatan setting set up,
We need some reference for this.
Yeah, this one maybe already says this. I can give you that.
Okay.
And this construction is kaya or no. All right. So the critical points detects non-trivial flow cohomology, and I spent much more time than I expected. Right. So now I want to explain you this diagram. This omega f.
W you see as a global function.
So this is
It's not a germ, it's a global function.
yeah, yes. Yes, W is a global function. But in the toric, in the SYZ case, somehow they kind of localize to each critical point. So you can do this at each critical point. I mean, even like Jacobian ring also localizes. If it's isolated, has isolated critical point. So this appeared in the previous talk, and so you can think of this as ZW, EZ1 is EZN, and so I just explained how you so let's say if X is how you define W in terms of disk counting. So if you have X to W, then somehow you expect this kind of diagram to hold. So this is called localized mere functor. So if we have any,
Why do you call it functor? So you have two infinity algebras.
yes, restrict to restriction of localized. Anyway, there is functor. Let me. Okay, this is called open closed map, and this is called Kodaira-Spencer map. And this is integration on X. This is the residue theory. And this is some multiplication by C times dz1 is dZn. Choice of isomorphism. And this is called bulk boundary map. Boundary bulk map. This studied by Polish Paintrov and Jacobian. Anyway, so let's look at the easiest part. So this open closed map is, so you look at holomorphic disks and then kind of look at the output of this disk operation. So this, the image of image of this disk somehow becomes defines a quantum cohomology. And actually, what I wanted to explain was this map. Unfortunately, I don't have much time, but maybe I can do it on Thursday. So, what is COB? This is closed open map, but with decoration B. So, the closed open itself is a map, something like this. Suppose you have some homology class of X, and you can look at disks intersecting A and then output. So this is the map from the homology class of ambient manifold to the Lagrangians. But when you put B, now we are now looking at disks with these bounding cochain insertions, these Maurer-Cartan insertions, and output. And the claim is that this with suitable assumptions, it's like that the image is multiple of unit. This is naturally an element of Jacobian ring of WB. So you might wonder why Jacobian ring suddenly appears. Well, this is just, let's say, polynomial ring divided by partial derivatives. So because these are like x, y, z, so you can imagine that, well, it's some polynomial. Maybe it gives you some polynomial, but so why the Jacobian ideal is relevant in this picture? But I don't have. Anyway, so just one picture. We have seen that this one, this is almost M1B. This is M1B of this guy. So this somehow naturally lies in Jacobian ring of W. So if you look at degenerations, and somehow this degeneration naturally lies in Jacobian ring with some suitable assumptions. And this diagram is known to commute in some cases, and this constant has some geometric meanings, and this is the equivalence of pairings on the symplectic side and the complex side. So if you are more curious, ask me later.
Can I ask you now, because I don't. Can you explicit? I don't know what to start.
Yeah.
The MKs from the previous discussions.
Yes.
How do they appear here? Can you
So-
define
so this one-
the first row, please?
In the first row.
Yeah, everything there. Can you define?
Okay, so open closed map is a map from homology to homology, but you can also do it
That's
by-
how
by
we're defining the homologies.
by inserting many. You can interpret it as a Hochschild cohomology because not only one class, but you can actually insert alpha 1 through alpha k. You can
And insert that into what?
no, sorry. Insert where? What I wanted to say was maybe from Hochschild cohomology to quantum cohomology is natural. You can expand this to some tensor products naturally from the Hochschild homology to quantum homology.
So let me ask, HFKK, is that given by the cohomology of M1?
Homology of
For the
M1.
Infinity algebra that we had
Right.
before.
But then when this is just a homology vector space, right? But then you for Hochschild chains, you'd have like multiple copies of this, right? So to say this is V, then you have V tensor K with some Hochschild differential. So this, you can also extend this to Hochschild differential kind of uses MK. A infinite Hochschild complex uses MK. And there is a map from here to here. Because you can just add more inputs, so just accommodate more things. And the other way around also, the closed open map also, not only you can just read one output, but you can also think of it as some Hochschild cohomology class. So this way you get some Hochschild cohomology. And these two, this is an infinite category, this is an infinite category of matrix factorization, digit category matrix factorization. This functor is an infinite functor relating infinite structure here and the digit structure.
What is PK?
This is mirror matrix factorization, mirror to K. And you have Lagrangian, you're supposed to have some matrix factorization mirror to it. And then there is a canonical infinite functor.
Is that a conjectural?
In this setting, there is a canonical one.
Which setting are we in? 3 examples? Or?
So this is what I call localized functor in this setting. So in the general set, when the mirror is, when W is given by this WB,
The setting is the third example.
yeah, in general. So when W is WB, you have an infinite functor from Fukaya category to MF explicitly given by.
What do you mean when W equals WB? We define WB, but we did not define W?
That's Landau-Ginzburg model. So
when we know the mirror symmetry conjecture,
when you know that mirror is given by this explicit construction of Maruka-Tan formalism, if the mirror is given by Maruka-Tan theory, then there is an explicit infinite functor taking Lagrangians to matrix factorizations. But I don't have time to, which is called localized mirror functor.
So you pick a Lagrangian to create the Maurer-Cartan and the potential, and then to any other Lagrangian you can associate the matrix factorization.
Yes. And just like here, it's very algebraic, right? So critical points and non-trivial homology is very algebraic, right? Like that, there is a very algebraic functor from any Lagrangian K to matrix factorization.
So you use the first Lagrangian to create a mirror,
Right.
and then
So we use L, and then for any other Lagrangian, so we use this L, and then if you have any other Lagrangian like this, if you have a Lagrangian like this, then it factors like x times y. It gives some factorization of x times y z. And if you have kind of complicated Lagrangians, then it gives matrix factorizations. Maybe I can explain on Thursday. Anyways, there is an infinite functor, and this is well studied, and this commits in good cases, and this commits in good cases.
what is the definition of quantum cohomology?
Quantum cohomology is when you have some cycles A and B. You can the classical cohomology you can define this cup product. But and for cup product is like Poincare dual to the intersection. So you have A, you have B, and they intersect. Then that's cup product. But quantum cup product is you have A and B, but now there is geomorphic sphere kind of. They don't have to meet. They commonly meet some geomorphic sphere. Then they have some quantum cup product. This is representing this the image of spheres, image of the like whole spheres that intersect A and B. So that's quantum cohomology. And it's an associative algebra, and if you set this formal parameterizing the area of homomorphic spheres to 0, then you get this one. All this one disappears. It's like that's why it's called quantum, because when you set t to be 0, then you get some classical coupling. So that's quantum cohomology. And there is this mysterious map in Jacobian ring. The product is just multiplication of functions, but this map is ring homomorphism, or often isomorphism. So that means this mysterious product is isomorphic to the standard multiplication of functions. And this picture can also explain that, but I don't have time.
I guess I have one last question. Are we going to explain in a different lecture all these maps again? Or this is
I can
take it from here as understand it from here, use it from here.
I can do that. I was going to do the double and the Symmetry, but can also do this if you want.
OC, for example.
Mm.
I'm still not clear how you define that.
OC, well, you still look at these disks, the modular space of disks, and if you have a class alpha, then you insert alpha, and then look at the image of this disk in the ambient space. So that defines some cycle, and the claim is that some chain, and the claim is that that's a cycle, and that this map. If you, for example, when you have a P1, this is Lagrangian. Maybe it doesn't help. So this output will probe the first disk will probe this part, and the second disk will probe this part. So